Hello everyone, and welcome to this Nordic Tech webinar about developing Thread products using nRF Connect SDK. My name is Jørgen Holmefjord, and I will be your host today. I've been working for 4 years as an application engineer in the technical support team in Nordic Semiconductor. With me today, I have my colleague Łukasz. Please go ahead and introduce yourself.
Hi, my name is Łukasz Duda. I joined Nordic Semiconductor almost 7 years ago, and I'm firmware engineer and thread team leader.
First, some practicalities. The duration of this webinar will be about 60 minutes. Questions are highly encouraged. You can enter questions in the top right sidebar. All questions are anonymous, and we ask you to please try and keep the questions relevant to the topic. We will answer questions towards the end in a separate Q&A session. The chat is not anonymous, and you should not use that for questions. If you have any other questions that's not relevant to the topic, please ask this on our DevZone support portal. After the webinar, there will be a recording made available on our webpage. If you missed it, we will recommend that you have a look at the Introduction to Thread webinar as well, if you're not familiar with the Thread protocol itself. The agenda today, Łukasz will start with an introduction to the software solution and the supported architectures in OpenThread. This will be about 10 minutes. Then we will continue with getting started. This will be more hands-on. I will show you for about 10 minutes how to use our development tools, setting up the toolchain and building an application using Sega Embedded Studio. Then we will have a longer session, about 30 minutes, where I will show you more advanced examples, building from the command line and configuring examples in nRF Connect SDK. And at the end, we will have about 10 minutes for a Q&A session. So then it's over to you, Łukasz.
Thank you, Jørgen. Let me start with introduction of main component of our Thread software, which is Thread stack, called OpenThread. In other words, it is software implementation of the Thread protocol. If you are familiar with Nordic's Bluetooth LE solution, OpenThread is equivalent to SoftDevice or Zephyr's BLE host with SoftDevice controller. This project has been started more than 4 years ago by Google, and Nordic from the beginning contributed our nRF52 platform that became the reference OpenThread platform, as well as officially certified one. Nordic also authored or co-authored several key core stack modules, which are required by the specification. This project is developed on GitHub, licensed under FreeCloudBSD, and obviously is fully open sourced. Thread stack is complete and optimized implementation of Thread specification in version 1.1.1, which allows you basically to create all possible device types. So whether you want to manufacture an end device, router, or border router, this is just simple configuration change. Thread 1.2 version of the specification is still under development, but already today you can use several of the features. It's worth to mention that OpenThread itself it's not only the stack, it's the whole project that contains several components which are useful to develop the Thread product. So for example, whenever you work on cloud communication or you are a border router designer, you can take the advantage of OpenThread border router implementation. This is reference Thread border router running on your PC, Mac, Raspberry Pi, or even OpenWRT. You can also use OpenThread Commissioner, which is cross-platform tool suitable to perform commissioning as defined both in Thread 1.1 and Thread 1.2 with commercial extensions. One of the useful components is OpenThread Network Simulator. It can be used to simulate thread networks, consist of tens of emulated POSIX nodes. As a product designer, you would like to have access to all tools needed to create firmware to your product. And so we combine multiple components and example applications and deliver software development kits, simply to shorten the time to market. And you have two choices. You can use nRF5 SDK for Thread and Zigbee, which is our market-proven comprehensive SDK, existing for a few years now. It can be used for products based on nRF52 family and Thread specification up to 1.1.1. However, keep in mind that this SDK is now under maintenance phase, meaning that the new features won't be added anymore. The second option, and the main star of today's webinar, is nRF Connect SDK that also supports Thread, and it's the way to go for new designs, especially if you want to have modern SDK with real-time operating system, or you plan to utilize new versions of Thread specification, or simply you want to use new microcontroller families, such as nRF53. nRF Connect SDK is basically extensible framework for building constrained but also advanced applications. If you want to know and learn more about our SDK, I encourage you to check our webinars where we describe both SDK and Zephyr operating system. Within nRF Connect SDK, you will find several components that are helpful for Thread product development. First, we have integrated OpenThread stack into SDK so that it interacts in an optimal way with our drivers, such as 802.15.4 radio driver. You can build Thread stack from sources, or you can take advantage of precompiled OpenThread libraries that we prepared with some most common configurations. The biggest advantage of using them is that you may get Thread certification by inheritance, reducing cost and your time. Next to the stack, you will find a bunch of examples presenting Thread applications, but also different architectures. So you don't need to start from the scratch trying to find the right configuration. One of the key distinguishing feature is that you can get support for protocol coexistence. So for example, you can run Thread and BLE protocols at the same time. Our SDK offers also the single code base for many technologies, and so reduces development time by delivering generic modules, libraries, and drivers, such as nRF security, which boosts cryptographic operations for Thread, or MCU boot, which ensures that secure boot is implemented in the correct and secure way. So let's talk now about the platform designs and recommended devices that you can use for them. First, your product can be built on the simplest one that we call single chip, single protocol architecture. In this design, the application layer and the Thread stack run on the same processor. The application uses OpenThread and IPv6 APIs directly. This design is mostly used for simple applications that don't make heavy computations, or battery-powered devices that act as sleepy-end devices. Due to low complexity, the overall cost of such solution is the lowest. In such architecture, to perform device firmware upgrade, you can use either dual bank DFU, sometimes called AB configuration, or external flash memory. When it comes to hardware, you can choose from nRF53 and nRF52 family, for example, nRF5340, nRF52840, or nRF52833. Another variant of a single chip design is a single chip multi-protocol architecture. It leverages some functionalities as a single file platform. However, additionally, it allows you to run both Thread and Bluetooth at the same time. This is possible because Bluetooth Low Energy Radio is complementary to Thread. BLE uses short periods of radio activity in regular intervals, while a thread uses all remaining time to work. So in practice, radio hardware is time sliced between those two protocols. However, this is completely transparent for application developer who can create Thread application completely separate to Bluetooth application. The set of hardware that you can use is similar to the previous option, although depending on your application, then nRF52833 device might not have enough flash size. Nordic supports also coprocessor designs, where next to our Nordic device, more powerful host processor is used, typically running Linux operating system. The standard network coprocessor or NCP design has thread features on the Nordic device and runs the application layer on a host processor. Typically, this host processor is more capable than the nRF device, although it has a greater power consumption. The host processor communicates with Nordic device through a serial interface, such as UART, USB, or SPI, using what we call spinal protocol. In this design, host controls thread device and communicates with it using full IPv6 packets. This architecture is useful for gateway devices or devices that have other processing demands, like speakers or IP cameras. One of the key features is that the high power or higher power host can sleep, while the lower power thread device remains active in the thread network. And finally, here you don't need to have the dual bank DFU or external flash, since you may incorporate a serial bootloader into NCP and perform DFU from the host. The second supported coprocessor architecture is called radio coprocessor or RCP. The major difference from the previous one is that host runs both application and OpenThread stack while communicating with a Nordic device that acts as a radio transceiver. In this design, RCP doesn't have enough information to perform mesh forwarding. So whenever RCP receive a frame, host processor must be woken up. This design is useful for devices such as video camera, which is always on to process some data. You can utilize our smaller devices for this architecture, such as nRF52811 or nRF52820. Also in this design, both devices send 15.4 MAC frames over spinal instead of full IPv6 packets, like in the previously showed architecture.
Thank you, Łukasz, for that introduction to the software solution and the architectures of OpenThread. In this section, I will show you how to get started with nRF Connect SDK. We will start by looking at some of our available development tools. The most important are, of course, the hardware development kits. We have the nRF52840DK and nRF52833DK. We also have the nRF52840 dongle. We recommend that you use the development kits for actual application development, as this has an onboard debugger built in on board. The dongle is very useful for use together with our development applications like the thread topology monitor and the nRF sniffer for 802.15.4. The thread topology monitor can be used to visualize a thread network, and this is using a CLI firmware to communicate between the application and the thread network. The sniffer is very useful for looking at the on-air packets and debug application to see what's going on air. If you are doing a multi-protocol solution, we can also recommend the nRF sniffer for Bluetooth Low Energy if you're doing a multi-protocol solution with Bluetooth Low Energy. If you want to use an IDE for your development, you can use Segger Embedded Studio. This is a specific Nordic edition for nRF Connect SDK. Segger Embedded Studio can also be used for debugging applications. If you are not using Segger Embedded Studio, you can debug application through a standalone debugger application called Segger Ozone. And if you're a command line user, you can also use JLink GDB to debug from the command line. I will start by showing you how to set up the toolchain. We will focus on nRF Connect application called Toolchain Manager, which is a simplified installation of nRF Connect SDK for Windows. We also have experimental support for Mac OS. If you're a Linux or Mac OS user, you can also use the Getting Started Assistant, which is another nRF Connect application. It's also possible to do a manual installation if you are requiring advanced options. So let's get started with some hands-on. You can find the documentation for nRF Connect SDK on our info center. Go to nRF Connect SDK under Software Development Kit. Then you can choose the version you're using. We will use the documentation for the version 1.4.0 release. If we open that, you can go to installing nRF Connect SDK through nRF Connect for Desktop. Here you have two options. You can use the Toolchain Manager for Windows, or you can use the Getting Started Assistant for Linux or Mac OS. So if you want to install the Toolchain Manager, you have to download the nRF Connect for Desktop application. So once that's installed, go ahead and open the application. Then you need to install and open the Toolchain Manager. Here we'll get a list of the available versions. We will install version 1.4.0. You can also change the directory if you want to place it at another location. We'll select Continue Installation. This will download and extract the SDK and the toolchain. Now that we have installed nRF Connect SDK and the toolchain, we would like to build an example to make sure that everything is working correctly. For this, we will use the Thread CLI example, which is available in nRF Connect SDK. This example demonstrates a minimal command line interface that is used to expose OpenThread configuration and data interfaces. What this does is that it translates ASCII string commands into OpenThread API to configure the chip. And this can be run over different serial transport. We currently have support for UART and USB CDC. And this CLI example is also used in Thread certification testing. We will build this example using Segger Embedded Studio. I will show you how to open an existing sample in Segger Embedded Studio from nRF Connect SDK. We will then build and flash this example to two separate boards. We will form a simple topology using these two boards through the CLI interface. I will then show you the topology using Thread Topology Monitor. And we will also see the on-air packets using the 802.15.4 sniffer. To make sure everything is installed and configured correctly, we will start by building one of the existing samples in Segger Embedded Studio. I have modified the CLI example with a single config to make sure that this is not automatically started. We will learn more about these configs later. In Toolchain Manager, press Open IDE to open Segger Embedded Studio. We will go to File, Open nRF Connect SDK project. Here we can select the toolchain release and version. We would like to build the Thread CLI example, which is this one. Next, we select the board name that we want to build for. Let's find nRF 52840DK. This one with nRF 52840 target. I've prepared two of these boards for this example. You can also select the build directory if you want to build somewhere else. And you can clean the build directory if you have been doing building before, since this is a new project, we don't need to do that. Press OK to run CMake and import all the projects and files into the Segre Embedded Studio. Once the project is loaded, you can browse the project inside Segre Embedded Studio. Open, for instance, the main file or on the other libraries that are built as part of this project. When you're ready to build, you go to Build and then Build Solution. Now that the example has completed building, I want to flash it to the two boards that I have prepared. Let's go to Target, download Zephyr/Zephyr.elf. I'll do this twice, once for each board that I want to download the sample to. I would now like to show you how to use the development tools that I presented earlier. Let's start with the sniffer for 802.15.4. In Wireshark, you can select the settings tool symbol next to the sniffer, and then you can select the channel that you want to scan on. Press Start to start scanning for packets. Next, we want to set up the thread topology monitor to show the topology of the thread network. Select the serial port where you flash the connectivity firmware, and you can select the channel. You can set the PAN ID and the master key. You can do a factory reset and set the polling interval and timeout. Press Start Scan to start scanning for devices. In the CLI, you have a shell. You can use OT help to show all the available commands. You can check the state of the device using OT state, and OT PAN ID will show you the PAN ID. OT PAN ID and then a new PAN ID will set a new PAN ID. You also need to set the channel to the one we used in the sniffer and the thread topology monitor if we want this to join the same network. OT channel 13 to set channel 13. OT IF config up will bring up the IPv6 interface, and OT thread start will start the thread stack. Now we'll see that the device will join into the network on thread topology monitor. Check the state, and this is a child which is consistent with the end device. Let's do this on the other node as well. Set the same PAN ID, and then we need to set the same channel 13, and bring up the IPv6 interface. OT IF config up, and then start the thread stack, OT thread start. Let's check the state of this device. This is also a child. We see that this first device now is promoted to a router. In the sniffer, we can check the packets that has been sent over the air. A COA packet, 802.15.4 packets, MLE packets. This is very useful for debugging things happening in your network. If we do OT IP address, it will list all the IPv6 address of the node. This we can use on the other node to ping the second node. OT ping and then enter the IP address. We'll send a ping request. You see that we received the response and that the packets are seen on the sniffer. You can also do a multicast ping with the OT ping ff03-::1. Now we get a response from both the other node and the thread topology monitor node. OT thread stop will bring down the thread stack, and after a while the device will be removed from the network, as we can see in thread topology monitor now. Now that we have made sure that the toolchain is working correctly by building an example in Sagra Embedded Studio, we will continue with some more advanced examples. First, we'll build the CoAP example, which consists of two different parts. It's one CoAP server example and one CoAP client example. We will build this example using a tool called West, which is provided by the Zephyr project. This has a simplified API compared to using CMake, and it can also be used for flashing examples to a board, and you can add your own commands if you want to. The CoAP client example we will also build with support for Bluetooth low energy multi-protocol solution. This will allow us to control the example from a mobile phone, which only support Bluetooth low energy and not Thread. And then Thread messages will be sent from the client to the server board over the Thread protocol. So we'll show some blinking of LEDs, both using the boards and from the mobile phone. Let's get started with some more hands-on. Now let's build an example using the command line. In the toolchain manager, press the arrow next to the SDK version you want to use. Then you can open bash or command prompt. For this exercise, we will use bash. Let's list the content of the root directory. This OpenThread samples are stored in nRF samples OpenThread. Here we have CLI, CoAP client server, and NCP examples. We'll first build the CoAP server example. Go to the root of the CoAP server directory. Then we do west build. We have to select the board with -B. The different board targets are listed in the documentation. We want to build for nRF 52840 DK again. So we input this into the west build as the board target. Now it will build the sample. Once the sample is built, we can flash it to the board using West Flash. And let's first check the serial number of the boards I have, West Flash, and then we use --SNR for serial number. Then input the serial number that we want to flash to. The second part of the CoAP example is the CoAP client. Let's change directory to the CoAP client directory. We can check the content. Here we have an overlay file for MTD and multi-protocol BLE configuration. This can be used to simply modify the example to build with different configuration. For this example, we want to use the overlay for multi-protocol. And we can do this by setting the overlay config. In the Zephyr documentation, you can find more information about this overlay config input parameter. Let's see how we input that into the command line. So you see, you can use --, and -D. And then overlay config, and then input the overlay config file name. So west build -B, and then input the board target again. And then if you want to, you can select a different build directory, --build -dir, and then set the name of the build directory. We'll do build BLE. And then capital D overlay _conf fig equals and then overlay multiprotocol_ble.conf. This will build with the configurations added in the overlay config file. We'll learn more about this later as well. So after complete building, we'll flash it to the second board. So west flash -- SNR and the serial number of the board. And we need to specify the build directory since we chose another one than the default. So now we have flashed the server to one board and the client to the second board. These are my boards. You can see that LED 1 is lit up, so this indicates that it's connected to the thread network. We can send a multicast message with button 2. This will turn on and off LED 2 of the board. Pressing button 4 on both boards will send a provisioning request, and this will allow us to send unicast messages by pressing button 1. You can still do multicast after you have provisioned. Let's reset the board, and now we'll test it the multi-protocol solution. I will open up my phone, and then I go to nRF Toolbox. I will set up an interface that looks like buttons. So I use the UART app, then configure, and I set input for these buttons, U for button 1, and M for button 2. Button 3 is not used in this example, but I will set it just so it looks like the buttons on the DK. And then we have button 4 is a P for provisioning. And then I press connect to connect to the board. I will look for the NUS co-op client example device. And then I can send messages to the co-op server, just like I did with the buttons on the board. This is happening over BLE. So by pressing 4 on the DK, I can do provisioning by pressing 4 in the app, and then we can also send unicast messages to the server. So this is sending Bluetooth messages to the client, and then the client is sending thread messages to the server. Once you get started with developing your thread application in nRF Connect SDK, you will see that there's a lot of different ways to change configuration parameters. Primarily these are kconfigs and device tree. In this part I will show you how to modify thread operational parameters like mode from full thread device to minimal thread device, etc. Channel and pan ID. Using tools like menu config and project config files. We will also show you how to do this in Segger Embedded Studio. We will also show you how you can configure the log levels of OpenThread and Zephyr using the menu config options. I will also show you how you can enable experimental support for Thread 1.2 using a project config overlay file. And we will use device tree to change the UART pin configuration of the nRF 52840. In the Zephyr documentation you can read about how the initial configuration is set. We will primarily focus on this project conf file, which is already present in the directory of the samples. Let's open the command prompt. We will open the co-op client example, and let's have a look at what's in the directory. Here we have the project config file. I showed you this briefly before when I said I set the configuration in the CLI example. Let's have a look at the project conf file. So here you can set various configuration that will be used when you compile the project initially. I would like to add some here. Let's change the pan ID and channel of the example. Then this is config underscore OpenThread pan ID equals, for instance, let's do 61453, and we can, oh, there's a typo. Config OpenThread underscore channel equals 15. Let's save this file, we'll use it again later. Now let's have a look at the overlay files. We used the multi-protocol one before when we built this co-op client examples. Let's have a look what it does. This enables the software's controller in nRF Connect SDK, so to enable Bluetooth Low Energy. And we also enable the Nordic UART service and different things required for Bluetooth. We also have a overlay file for enabling minimal thread device, if you want to do a sleepy end device, for instance. So these configurations are set to achieve that. Once you have built the example, you can also use menu config to change the configurations. So let's have a look at the documentation in the interactive kconf interfaces. So this is the menu config. We can start it by doing west build-t menu config. So let's do that now. Inside menu config, you can browse the menus to find a lot of different configurations. For instance, we can find the configuration for OpenThread. So this is thread network configuration. Here you can set the pan ID. For instance, if we want to change this, let's set it to, for instance, 61453. We can also change the channel. And like that. Another feature of the menu config is that you can search for configurations. If you don't know where in the menu it is, you can type / and then you can search for example, OpenThread, and it will list all the OpenThread configurations. If you want to do OpenThread logs, you can type OpenThread log, and you can set the different log levels for OpenThread. This can also be used for other modules. If you want to, for instance, enable nRF X drivers, you can search for that, much easier than browsing through the menus. If you want to have a look at more information about the config, for instance this one, you can type question mark, let's see, enter, and then you can do question mark, and it will show you information about this kconfig. Note that all the configurations that you do in the menu config will be lost if you do a pristine build, so they are stored inside the build directory. Let's have a look at the configurations that we just modified. Inside the build directory, it's located in build, and then Zephyr and that .config. So let's see if we can find the pan ID that we just set. Yes, here we have the pan ID and the channel. If you want to do the same in Segger Embedded Studio, you can do that inside the IDE. Let's have a look. Here I have opened the co-op server example, and we can go to project, configure nRF Connect SDK project, and I can filter on OpenThread pan ID, and here I can change the pan ID. Let's set the same as we had before, 6543, and the channel, let's set this to 15, and then we can click configure, and this will run CMake again to update the configurations. Let's have a look at the configurations again. OpenThread and CD co-app server. The build nRF 52840 DK _ nRF 52840 is for the Segger. So let's have a look at the config. Build server and that's config pan ID, and we can see that now the pan ID is also set for this example. So let's build these examples. For the client, I would like to also show you the overlay. We used this before, but let's do it one more time. So west build -b nRF 52840 DK nRF 52840, and we can set a new build directory. -d is the shortcut for that. Build _mtd, and then we do -d overlay _config equals overlay mtd.conf. I've now built and flashed the examples to the two boards. The left one is running the client example, and the right one is running the server example. The client example is running a minimal thread device, so it does not have the shell anymore. The right one, the server, still has the shell. We can use that to check the configurations that we just set in the menu config and project config settings. So to do that, we use OT pan ID to check the pan ID. So this is set correctly. And then we use OT channel to check that the channel is set correctly. So if we do OT router table, this will only show one device since the client is running in minimal thread device configuration. And then if we do OT child table, this will show the second node, which is the minimal thread device or the co-op client. One of the new thread features that are only available in nRF Connect SDK is support for Thread 1.2 extensions. We currently have experimental support for this in nRF Connect SDK version 1.4.0. This can be enabled by setting some kconfigs. If you set the thread version number to 1.2, it will enable enhanced frame pending, enhanced keep alive, and thread domain name features. You can also enable additional features like domain unicast address, multicast listener registration, and enable backbone router by setting these configurations. These are kconfigs, so you can add it either to your project conf file or using an overlay file. In the CLI example, there's already a ready-made overlay file for enabling this. Let's have a look at that. So you can see that it sets all the kconfigs. I have already built this example inside the build thread 1.2 directory, but we can also, if you want to build it, you can do that using west build. So then you add the -d overlay config and then input overlay that you want to use. Once you have built this, we can have a look at the build directory to see that the configurations are included in the config file. And here you see we have the thread version set to 1_2. If you would like to learn more about the different configuration options, there's a full kconfig reference in our nRF Connect SDK documentation. If you would like to change configurations that are specific to a board or a device, you can do that using device tree. So the simplest solution is to use device tree overlays. You can put that in the board's directory inside the project, or you can specify it manually, or you can add the board overlay directly in the application folder. Let's have a look at the CLI example. CLI. Here we have already a boards directory. And this contains two files, one for the 833 DK and one for the 840 DK. Since we're building for the 840 DK, let's modify this file to modify some configurations. This is useful for setting configurations like pin settings for serial interfaces or configuring ADCs, etc. So basically things that are not specific to a project. Let's do TX pin and set it to, for instance, 30. And then we can do the RX, let's see, RX pin for, this is for the UART interface. We had a lot of questions about this in nRF 5 SDK. How to change the pin configurations, and there you had to do a full recompile of the OpenThread libraries. So I want to show you how to do it in nRF Connect SDK. We can also do current speed and set that to, for instance, 1 megabaud, just to mix things up. So let's save, exit, and then we build this one. Let's do west build dash B 52840K. So set target build, and then set a new build directory. Now that the build is complete, let's have a look at the compiled device tree file. This is located in the build directory in Zephyr Zephyr.dts. You can look for the UART 0, for instance. So here we can see that we have set the new speed and the TX and RX pins. Let's flash the example. I have now connected the UART pins from 30 and 31 to 6 and 8 on the DK, as you can see in this image. And then we will change the baud rate from 115200, which is the default, to 1 megabaud. So let's see, open the terminal, and now we can see if I reset the board, it will print the correct data. If I unplug the pins that you saw in the picture, nothing is working. If I reset the board, nothing is printed. So we see that the configuration is applied correctly. If you want to make any changes to the device tree when using Sager Embedded Studio, I would still recommend that you modify the device tree overlay files outside of the IDE. If you have modified overlay file, you should afterwards go to project and then run cmake in order for the changes to take effect in the project.